So, my dear friends, good morning. We'll start 574 from where we left. 11. Pressure test. A pressure test conducted on the service piping may function as a leak test, or if the pressure is high enough, it can reveal gross errors in the design of fabrication. Underground lines, rather inaccessible piping, water and other non-hazardous utility lines, long oil transfer lines in areas where leak or spill would not hazardous to personnel or harmful to the environment, complicated manifold system, small piping and tubing system, all system after chemical cleaning operation and required by jurisdiction. Performing pressure test. During liquid pressure testing, all air should be expelled from the piping through vents provided at all high points. If the system is not full of liquid, the trapped air will compress. With large quantities of a compressible medium in the system, a failure will be more violent than in a liquid full system because expansion of the compressible medium. Care should be taken to ensure that the test doesn't overpressure the system, including components, expansion joints that may have a lower design pressure than the remainder of the piping system. Calibration pressure gauges properly located and the proper range should be used and carefully watched during pressuring. Various fluids can be used for pressure testing. The following are most commonly used: water with or without inhibitor, freezing point depressant or wetting agent. Liquid products normally carried in the system if they are not toxic or likely to cause fire in case of liquid or a leak or failure. Steam, air, carbon dioxide, nitrogen, helium, or other inert gas. ASME B31.3 has restriction on the use of test mediums listed in item C and D. Water may not be suitable as a test fluid in some piping systems such as acid lines, cryogenic systems, air dryer systems. Uninhibited salt water can cause corrosion of some non-ferrous alloys and SCC of austenitic stainless steel. Salt water can also cause corrosion of ferritic steel and severe pitting of austenitic steel, such as valve trim or plating. Most natural waters contain bacteria that can lead to microbiologically induced corrosion. The water is left in the piping for too long after a pressure test. Austenitic stainless steels have failed after 2 to 5 weeks of this kind of exposure. Water can freeze in cold weather unless a freezing point depressant is used. The depressant should not be harmful to the sewer system or other place of disposal. Steam is sometimes used to warm the water, prevent freezing. The transition temperature of the steel should be considered to prevent brittle failure, and the testing is during cold weather or with acid fluids. Pneumatics test in conjunction with soap solution, foaming agent, or sonic leak detector are sometimes permissible for some lines and systems. The preferred medium for pneumatic testing is an inert gas. Compressed air should not be used, but flammable fluid can be present. Leaks that would not detect during the liquid pressure test can often be detected by pneumatic test. Because nitrogen and helium are more penetrating than air, they are used when service conditions are particularly critical. Filling any piping system with an inert gas creates an asphyxiation hazard and every stage in the process. Precautions must be taken to ensure that no personnel are inadvertently exposed to low oxygen atmosphere. Pneumatic testing should be conducted strictly in accordance with ASME B 31.3. All precautions specified in ASME B 31.3 should be strictly observed, including the elimination of conditions under which brittle fracture might occur. Hammer testing. Hammer testing of piping valves and fittings for thickness is a largely outdated test method in which the component is struck with a hammer in order to listen to the sound of attenuation. The type of sound can be used by an experienced inspector in hammer testing to differentiate thin metal from thicker metal. Individual sites may choose to allow hammer testing of certain lines but should do so only after evaluating the hazards involved and assessing whether the hammer strikes will damage the piping or cause a leak. Hammer testing is still considered a valid test for support anchor or flange bolt tightness by tapping on the nut and monitoring for movement, identifying other loose or broken parts, checking the piping to ensure that it has drained properly of liquid or if it contains excess corrosion scale, process or corrosion scale, tapping the pipe and hearing the dull thud rather than a ring attenuation is an indication of a problem. Telltale hole drilling. The effort to assess sentinel holes or Delforage holes is the application of small pilot holes 1 by 8 inch 3.2 mm diameter drilled into the pipe component while using specified and controlled pattern and depths. The purpose of telltale holes is to prevent major incidents associated with the undetected thinning damage due to internal corrosion, erosion corrosion by alternating unit personnel with a leak through the telltale holes. Telltale holes are less effective when isolated heating is occurring. Telltale holes are used in conjunction with typical detailed piping inspection programs, although they may provide an added measure for protection against major ruptures. Above grade visual surveillance. Indication of leak in buried piping can include moist ground or actual seepage of product carried in the underground piping. A change of surface contour or ground discoloration of soil, softening of paving asphalt, pool formation, bubbling water puddles, a noticeable odor. Surveying the route of buried piping is one method to identify problem areas. All lines should be inspected at just below the point when the entire earth, asphalt, or concrete since serious corrosion frequently occurs at such locations. Close interval potential survey. Close interval potential survey are used to locate corrosion cells, galvanic anode, stray current coating problems underground contracts areas of low pipe to soil potential and other problems relating to cathodic protection. A closed interval pipe to soil potential survey measures the potential of the pipe to soil directly over the pipe at predetermined intervals between the measurement, usually 2.5 foot, 5 foot, 10 foot, 10, 20 foot, 0.8 meter, 1.85 meter, 3 meter. Or 6 meter. The pipe contact can be made at an above ground pipe attachment. An example of a standard pipe to pipe soil potential survey on a bare line is shown in figure 29 and figure 30. Corrosion cells can form on both bare pipe and coated pipe with holidays, where the bare still contacts the soil. Since the potential at the area of corrosion will be measurably different from an adjacent area on the pipe, the location of the corrosion activity can be determined by the survey technique. Underground piping corrosion beneath poorly applied tape wrap. Pipe to soil internal potential survey used to identify active corrosion spots in underground piping. Bare line, no cathodic protection. Holiday pipe coating survey. Soil resistivity checking. Resistivity ohm cm 191.5 into D into R. The number 191.5 is a constant that takes into account the mathematical equation for the mass of soil and conversion vector to convert feet into centimeters. D is the distance in feet between any equally spaced pins with the pins in a straight line. R is the resistance factor of the voltage drop across the two inner pins divided by induced current flow in the earth between the two outer pins. The depth that pins are inserted in the earth should be small compared to the pin spacing. The following conditions should be considered in 4-pin soil resistivity measurement. Underground structures should be excluded from the measurement. All the pins should be in a straight line and equally spaced. The depth of the pins inserted into the ground should be less than 4% of the spacing. The soil resistivity meter should be designed to exclude any effect of extraneous AC or DC currents. Use a standard rod bar to provide an initial hole, avoiding additional water during the after opening of the hole. Applying pressure on the soil bar after insertion into the open hole. Winner 4-pin soil resistivity test. P equal to 191.5 into D into R. D is the pin spacing, R is the meter reading after balancing. E is the rho, soil resistivity, ohm cm, ohm centimeter. For measuring resistivity of soil samples from auger holes or excavations, a soil box serves as a convenient means for obtaining accurate results. Soil box is used to determine the resistivity of soil from a certain location by removing the soil from its location and placing it into a soil box. If the resistivity of the soil sample is not going to be measured immediately after the removal, soil should be stored in a container that can present its moisture and prevent it from contamination. It depicts two types of soil box used for resistivity measurement. Important points for consideration when using soil box include avoiding contamination during soil sample removal, handling, and storing, avoiding adding or subtracting water, having to compact the soil sample to same density in the soil box as it is prior to removal of the ground. Intelligent pigging, video camera guided leak test with inspection, new fabrication. All subject covered in sector should meet the principle of ASME B31.3 or equivalent pipe fabrication standard published by Standard Development Association SDO. ASME B31.3 contains a formula for determining the required thickness of new uncrowded straight pipe subjected to internal pressure. API 570 permits the use of simple Barlow formula for determination required to wall thickness of the servicing piping. ASME B31.3 provides guidance of when other equations are applicable. The Barlow formula is as follows: T equal to PD by 2HC, where T is the pressure design thickness of internal pressure in inches millimeter. P is the internal design gauge pressure of the pipe in pounds per square Square inch D is the OD of the pipe in inches, millimeters. S is the allowable unit stress at the design temperature in pounds per square inch. E is the longitudinal quality factor. The Berlo formula gives results are practically equivalent to those obtained by more elaborate SMB 31.3 formula, except the cases involving high pressure where thick walled tubing is required. Metallic pipe, for which T is greater than D by 6 or E by SC greater than 0.385, requires special consideration. SMB 31.3 also contains the allowable unit stresses to be used in formulas contained in that publication. This allowable stress include a factor of safety and a function of pipe material and temperature. Structural minimum thickness. The owner user shall specify how structural minimum thickness are determined. An example of table calculated structural minimum thickness for a straight span of carbon slab piping. Table 7. Additional consideration and allowances may be required for following conditions: screwed piping fittings, piping diameter greater than 24 inch, temperature exceeding 400 degrees Fahrenheit, higher alloys other than carbon steel, spans in excess 20 foot, high external loads, refractory line pipe that also used to support other pipe, rigging loads, personal support loading, excessive vibration. Calculate the pressure design thickness for rating. So determining the minimum required thickness of NPS2 ASTMA grade 106 grade B, designed for 100 psi 100 degrees Fahrenheit, and D equal to 2.375 2 inch, and S equal to 20,000 psi, E equal to 1 since seamless, Y equal to 0.4. They calculated ZT 0.006. The NPS2 pipe is 100% supported is laying flat ground. Then 0.006 inch would hold 100 psi of pressure. This thickness include 3 to 1 safety factor. However, it would not hold up in the pipe rack. Step 2. Determine structural minimum thickness as per owner user table of engineering calculation from table 6. Default structural minimum thickness is 0.070. The larger of major design thickness or structural minimum thickness. Table 6 default structural. Minimum thickness is 0.07. Select the minimum required thickness. This is the larger of the pressure design thickness, and determine the minimum required thickness of 14 NPS ASTM A106 grade B pipe designed for 600 psi. Minimum thickness is 0.110 and T is 0.208. That is example 2. So 0.208 inch. The table 6 we have to read. Table 7. Microwave. Gigahertz terahertz microwave used to determine laminar non-fusion, kissing bonds, and impact damage. Has detected ingress of fluids into the substrate in woven metal. Techniques has ability to detect response at non-metallic and metallic interface, unable to inspect through any metallic cladding or coating. Has been used to detect gross wall thickness changes due to erosion and significant lack of adhesive bond joint. Sensitive to surface near surface flaws, doesn't reveal through wall damage or thick wall piping. Limit of detection at relatively high with 0.25-inch difference between wall thickness and disbonded areas measuring 3 inch. Takes a function of thermal differential. The process steam is significantly different in temperature than surrounding ambient temperature. The good profiles can be obtained. Alternate approaches are to introduce heat into the area. Examination, monitor the rate of decay in relation to good samples. Material property used to identify proper curing and long-term degradation of the resin. Most common hardness reference ASTM D2583. Barcode hardness test method used to determine the hardness of both reinforced and non-reinforced rigid practice limited by available area. Small diameter bore pipe works in with inhibition can yield lower hardness values. The wide range of flaws can be detected. He has been used to vessels and tanks constructed from FRP many years, and these procedures have encompassed typical flaws identified include adequate structural integrity due to okay. Some of the basic this table 6. My rating table 6. Okay, I have to check. Maybe table 7. It's fucking idiots. Default minimum structural thickness. It's still not changed. This should be 7. 14 NPS. So 14 NPS minimum thickness 0.11. That is what they are writing. So you take 0.28. In case of here, it is NPS2. So if NPS2 is 0.07, so you take the higher value, that's all. Thank you, gentlemen. And now let us see. Circle numbers indicate point at which thickness should be monitored. Sketches. So it is starting from here. 1, 2, 3, 4, 5, 6, 7. Then 8, 9, 10, 11, 12, 13, 14, 15. The 16 should be here. Don't know why this is there. Should be somewhere here. 16. Decoking line. 16, 17, 18. Maybe something like this. Or 16, 17, 18, 19, 20, 21. There may be more. Review of records. Records of previous inspections and inspection conducted during the current operating period should be reviewed soon after the inspection are conducted to schedule the next inspection date. The identification, piping, vessel description, inspection interval, designation condition, operating condition, remaining life, set by last reading, next recommended inspection date, point, reading, location, size, limit, thickness, method, month, initial reading, year, inspection, temperature, thickness, method, month, year, inspection, temperature, subsequent reading like that. So there is a format they given. The external checklist for process piping inspection. So what you have to check that given an X-ray. Thank you, gentlemen. We'll stop.